Hi everybody. So in this video, I'm going to show you how to carry out a hypothesis test for a binomial distribution. So we'll work through a couple of examples and then we'll try some exam style questions. And if you want to work along with me, you can download this PDF from my website. I'll leave a link below. So in our first example, we're told that a factory tests a new method for making screws, and 20% of the screws made by the factory are known to be defective. A random sample of 20 screws is checked, and 2 are defective. Show that this does not provide evidence at the 5% level of significance that the defect rate has decreased. We need to state our hypotheses and calculations clearly. So the first thing I'm going to do is I'm going to state our hypothesis. Our null hypothesis, HO, is always going to be that the probability equals what we're told. And this is what we're testing at the 20%. So P equals 0.2. Our alternate hypothesis is given in the question, and we're told that the defect rate has decreased, which means P is less than 0.2. And then if we state our distribution, that X is distributed binomially with 20 trials and a probability of 0.2. And we need to define this random variable X. So I've said that X is the random variable, the number of defective screws. Then I find it really helpful to sketch a binomial distribution. This helps me to identify whether it's a one-tail or two-tail test and in which tail we're looking at. And this line here is the expected value, which is the probability multiplied by the number of trials. So the expected value of X is 10. And then because we're looking at P being less than the 0.2, we're looking at the tail to the left of the expected value. So we're looking at this region here. And this is our critical region. So if the value of X falls inside of this region, we reject HO and we accept H1. If it falls to the right of this line, this critical value, then we accept HO. This is our accepted region. So I label this as having an area of a significance level, which is 0.05. Okay? So what we need to find then is the probability of X being less than or equal to this 2. And we can check this on a calculator. If we go home and then distribution, we want binomial CD, we want variable, we want our X value to be the 2, the number of trials to be 20, and a probability of 0.2. We'll execute this and we get 0.2061 to 4 dp. And this is clearly bigger than the significance level. So this 2 would be over here somewhere, okay? So now we need to write a conclusion. So we'll say because the 0.2061 is greater than the significance level of 0.05, we accept HO. And that the new method has not reduced the defect rate of 20%. So it's really important that our last sentence always relates back to the context of a question, okay? Let's try another question. So in this question, we're told that a farmer tests a supplier's claim that 90% of seeds germinate. He plants 18 seeds and 14 germinate. At the 5% significance level, test whether there is evidence that the germination rate is lower than claimed. We need to state our hypotheses and calculations clearly. So we'll go through the same process. We'll state our null hypothesis. What do you think this will be? So that P will equal 0.9. And our alternate hypothesis is that the germination rate is lower. So P is less than 0.9. Now if we define our random variable, we'll say that X is distributed binomially with a number of trials at 18 and a probability of success 0.9. What do you think we'll define this random variable as? We'll say that X is the random variable with number of seeds which germinate. And then if I sketch the binomial distribution, our expected value will be 0.9 times the 18, so 16.2. Now, which tail do you think we're looking at? Do you think we're looking at to the left or to the right? Well, because p is less than 0.9, we're looking to the right. And you can see this works because the 14 is less than the expected value. So we're looking at this region here as our critical region. And this has a probability of 0.05, which is the significance level. So what we need to find is the probability of X being less than or equal to the 14 which do germinate, and then to see whether that falls to the left or to the right of the critical value. So if we go back to our calculators, we'll clear this. We'll say X is 14. We've got 18 trials and a probability of 0.9. Then we'll execute that and we get 0.0982 to 4dp. So now we can write our conclusion. Because the test statistic is greater than the significance level, we accept HO. So what do you think our conclusion will be relating back to the context of the question? We'll say there is significant evidence to support the farmer's claim that 90% of his seeds germinate. Okay? Let's try some exam style questions. So now we're told that Stephen works in a call center. He knows from experience that on each sales call he makes, there is a probability of 1/6 being successful. Daniel claims to have a higher success rate. A colleague tracks Daniel's next 35 sales calls and finds 11 are successful. We've been asked to test at a 5% level of significance whether there is evidence to support Daniel's claim. And we need to state our hypotheses clearly. So do you want to try this question yourself? You can pause the video and come back when you're ready. Okay, so I'll come back if you want to go. So we'll state HO as P equals 1/6 and H1. And because we want a higher success rate, H1 P is greater than 1/6. X being distributed binomially with 35 trials and a probability of 1/6. And now because P is greater than 1/6, we'll work out the expected value as 35 multiplied by a 6, which is, and then because P is greater than 1/6, we're looking to be right. So now this will be our tail here. And again, the significance level is 0.05. So now we need to work out the probability of X being greater than or equal to 11. And this will equal 1 minus the probability of X being less than or equal to 10. So if we go back to our calculators, we'll say that X is 10. We've got 35 trials and probability of 1 divided by 6. And this will give us 1 minus 0.9768. So if we go home and calculate, we'll have 1 minus the answer, and we get 0.0232. Okay? And this is our test statistic. And because the 0.0232 is less than the significance level of 5%, we reject HO. Can you see that this 11 then would now fall inside of this critical region? So our conclusion would be there is insufficient evidence to support Daniel's claim. Let's try one more question. So finally, we're told that a factory finds that 10% of light bulbs are defective, and after modifying the process, a sample of 20 bulbs is tested and one is defective. At the 10% level of significance, test whether the defect rate has changed and to state our hypothesis clearly. So now we're looking at a two-tailed test because we haven't been told whether the probability is greater than or less than. So we need to check for both. So do you want to try this question yourself? You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So we're saying that HO, P equals 0.1, and then our alternate hypothesis is that P does not equal 0.1. We're saying that X is distributed binomially with 20 trials, and that probability, where X is the random variable, the number of defective bulbs. So the expected value will be the 0.1 times 20, so this will be 2. And then because one bulb is found to be defective, the tail we're going to look at is to the left of the expected value. But we need to say, because it's a two-tailed test, this significance level is shared equally between these two critical regions. So each of them has a probability of 0.05. So now we need to find the probability of x being less than or equal to 1. So now if we go to our calculators, we'll choose x as 1, n as 20, and p as 0.1, and we'll get a probability of 0.3917. So our conclusion then is because the test statistic is greater than the significance level, we can accept HO. The defect rate has not significantly changed after modifying the process. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.